On the subject of inelastic collisions, the second special case I'd like to look at is what I'll call the explosion or a reverse collision. This is a case in which the work done by non-conservative forces is positive, increasing the mechanical energy of the system. So as an example, let's consider, say, a pumpkin sitting here at rest that we're going to blow up. Stick a little firecracker inside that pumpkin, and here, before the firecracker goes off, the pumpkin's at rest, the momentum of the system is zero, the VCM is zero. Firecracker goes off, blows the pumpkin into these three chunks that go flying off in three directions. In this case, our center of mass is still in the same spot. It's going to remain still, our VCM will still be zero because no external force, so no external impulse is exerted on the system. The firecracker comes from inside the system. It's internal. The forces that the expanding gases produced by the chemical reaction that occurs when the firecracker detonates, those expanding gases push on these three chunks, doing work on those three chunks, but those would be internal forces. So there's no external force here. The momentum of the system would be conserved. So if it's zero beforehand, it's zero afterwards, and the VCM stays zero. Okay, so the center of mass doesn't move, but the three chunks all fly off, each with their own momenta, and we can express conservation of momentum like this. If the initial momentum of the system was zero, then the final momentum of the system, being the sum of the momenta of the three chunks, the sum of those must be zero also. So that's the real key to analyzing an explosion like this. If the object starts at rest, then the sums of the the sum of the momenta of the pieces must all be zero, must come to zero. In particular, if there were just two chunks instead of three, so just B and A, in that case we could see that the two chunks that blow off must have equal and opposite momenta if the pumpkin started at rest. So that's an interesting feature of an explosion. Two pieces go off, they must have equal and opposite momenta. If we were to try and solve for those final momenta or velocities, we'd have to look at energy as well. We're noting that the work done by non-conservative forces is positive here. So the change in the kinetic energies is positive. There's a net gain in kinetic energy for all those three pieces. Where's that energy coming from? It would be stored non-mechanical chemical potential energy in the firecracker that is converted to the kinetic energy, increasing the mechanical energy of this system. Okay, if we were to try and solve for those final momenta, I think we can easily see here that there's not enough information in general. You would need to know how much energy is going to be released by the explosion, how much stored non-mechanical energy is going to be converted into mechanical energy. You need to know that ahead of time in order to have any hope of computing, a hope of predicting these final momenta. Not an easy problem in general. The third special case is not that different. Really, we could just consider this an extension of our explosion, but I'm going to call it the engine-driven system. Here again, we've got a type of reverse collision in which non-conservative forces do positive work, increasing the mechanical energy of the system. Suppose their system consists of a person on a skateboard moving to the right, and then at some point the person jumps off of the skateboard, making a leap to the right, pushing the skateboard backwards to the left. Okay, if the force exerted on the skateboard by the person were horizontal only, that is, no vertical forces to worry about, if the forces were only horizontal in this explosion here, as one object becomes two objects, like a reverse, completely inelastic collision, then the momentum of the system would be constant, and the VCM here would be the same before and after, so that imaginary point, that center of mass, would continue to move with the same velocity after the person and the skateboard separate. We could set up conservation of momentum here. Initially, one object with this total mass moving at a velocity, the VCM. Afterwards, these two separate objects with their two separate velocities. So two separate final velocities, only one equation. Could we predict these two final velocities? The answer is no. In general, there won't be enough information here. If we look at conservation of energy, we can see that the work done by non-conservative forces, that would be increasing the kinetic energies, or I suppose changing the kinetic energies of our two objects, not necessarily increasing since we were moving at the start. But there will be a net increase in mechanical energy here as stored non-mechanical chemical potential energy, this time in the rider's muscles as opposed to in the fuel of that firecracker, gets converted into kinetic energy. My main point here is to look at this version of an explosion and recognize that the source of energy that will be converted into kinetic, the source of the energy comes from the rider, the muscles storing chemical potential energy. So I want to think of our rider here, our person, as a kind of engine, a system that is storing non-mechanical energy that could be converted to mechanical energy if that system does work. Like if the feet push off of the skateboard, doing work on the skateboard, they're converting non-mechanical into kinetic. More broadly, an engine is any system that will convert stored non-mechanical energy in the form of fuel, such as gasoline, or in the form of a battery, the sort of electric potential energy stored in the chemicals of the battery, or in your muscle tissue, if it's an animal or a person. We could consider any system that's drawing stored non-mechanical energy from this, or this as an engine. So a person, an animal could be an engine. And the system converts that stored non-mechanical energy into mechanical energy by doing positive, non-conservative work. So a car, for instance, is storing non-mechanical energy in the form of its fuel here. This could be a gasoline fuel tank in an internal combustion engine, or it could be a battery in an electric car. And that is the source of the energy that gets converted into the kinetic energy of the car. So when our engine does non-conservative work here, it can convert that stored energy into kinetic. So that can happen if expanding gas in your internal combustion engine pushes on pistons, does work on the pistons, which in turn rotates the axles of the car. That's the work that would be being done there. If this was a battery, then the electric potential energy being stored there would do work by driving a motor that turns the axles of your car. So the engine is doing the non-conservative work that is pushing on the pistons or moving the drive system of your car. This is where the energy comes from that becomes the kinetic energy of your car. I'm stressing that to make the point that the force of static friction that the ground exerts on your tires, if your tires have good traction so they're not slipping, so static friction that pushes your car forward, that is imparting an impulse, an external impulse on your car, adding momentum to your car, doing pseudo work on your car. But these forces are not doing actual work. The ground is doing zero actual work on your car, which makes sense because the energy that your car gets doesn't come from the ground. Your car doesn't draw its kinetic energy from a reservoir in the ground. It's getting its mechanical energy from the engine here. So it's the engine that's doing the non-conservative work, the engine that's transferring kinetic energy to your car, while the ground is indeed transferring momentum to your car via these two forces right down here. So, okay, maybe you're looking at this car here and thinking this isn't really a collision at all. And I see what you mean. We can think of it, though, as perhaps like a reverse collision, like an explosion, much like this person pushing off of the skateboard. The person is the engine, converting stored energy in the muscles into kinetic energy, pushing off of the skateboard. It's a push-off. And here the car is pushing off of the ground. So it would be the planet Earth here, which is like the skateboard. Car moves to the left as it pushes the whole planet Earth off to the right. So in that sense, it still is a kind of a form of reverse collision. And everything I've said about the car pushing off of the ground also applies to you walking on the ground. When you walk across the floor, your kinetic energy doesn't come from the floor. You're not drawing energy from the floor. Your kinetic energy is coming from the stored energy in your muscles. You are the engine. The muscles, your muscle tissue, is doing non-conservative work on your skeletal system to add the kinetic energy to you to move you across the floor. Your feet pushing off of the floor, that traction that you get from these forces of static friction between your feet and the floor, that is imparting an impulse to you. That's doing pseudo work on you. That's giving you your momentum as you walk across the ground. But it's not giving you your kinetic energy. You're not drawing kinetic energy out of the ground. You're drawing it from your fuel source here.